Okay. So zooming now, view, go to full screen. Yes. Full screen here, and this goes here. Okay. Okay. So yes, we are good. So, all right. Any questions or comments from last lecture by any chance? Okay, so I'll start, and then if you have something to say, we can just discuss it later on. So let me just continue by an example. So this has to do with counting lattice points. First, we can do it in R2, but then we can do it in general. So, so let's consider kind of a portion of Z2 lattice. And let's take a circle of radius root r. Okay, so we are interested. So we are interested in this number. So let ZR, by definition, be the set of all pairs M and N belonging to natural numbers cross natural numbers such that M2 plus N2, I would say, is less than or equal to R. Yes. So n natural numbers for me does not contain zeros. So let me just make my convention is 1, 2, 3, and if I write n 0, it means n union 0. So that's just a notation. Just to be clear. Okay, so ZR is really the number of such things, and not the set itself. The number of such things. And it's important to have an estimate of this number of lattice points, which are strictly positive in both coordinates, that are located in this first quarter or first quadrant circle of radius root r. So as you can guess, this number is approximated by the area of the circle. And we want to show that the ratio of ZR, so let's take AR equal to area of quadrant circle. This area. And our goal is to show that ZR over AR goes to 1. That's just it's like it could be even a high school problem, right? It's nothing fancy here. Everything is very, very clear. And we want to show that this is the case. So there are different proofs of this fact. So the most elementary is the following. So let's define a map for each pair Mn. You define square Smn. So that's square. Such that this point Mn is in the top right corner. Mn at top right corner. Okay, so if you have a point like this, then you just take this square. If you have a point like this, which is already inside that, then you just take this square. Right? this point you attach this square, so on, right? Okay, so when you add all these areas, obviously the sum of these areas is less than area of the circle, right? So this immediately we have that ZR is less than equal to AR, right? But also we can focus on those squares that intersect the boundary and so on. Maybe this one here also. So the difference between AR and ZR is exactly the number of squares that intersect the arc of the circle. So the other estimate we have is that AR minus ZR is equal to number of squares that intersect circle. And this number, you can convince yourself easily that this is going to be proportional to the length of the circle. That's not difficult to see. So this number is actually at most is less than equal to C root R. C is just a constant for now that it doesn't matter for us, this constant C right now. We just, okay, so from here, then you get that, yes, ZR is bigger than equal to AR minus C root R. So you have an estimate on both sides like this. So we have got ZR less than equal to AR and bigger than equal to AR minus C root R. Okay. So now you can divide ZR by AR. By AR is less than equal to 1, and this is bigger than equal to 1 minus C root R over AR. But we know what AR is. AR is pi root R squared over 4 equal to pi R over 4, right? That's what, this is the area of the circle of radius R, radius root R, but divided by 4, because we're just looking at quarter. Okay, so this quantity is R, of the order of R, this is root R. So if you take limit as R goes to infinity, you get 1. So then we get that, limit of ZR over AR as R goes to infinity is equal to 1. And in fact, this sort of estimate is valuable because it says, if you are a little more careful with estimating, it says that the next term in the approximation, so it looks like the first term in the approximation is R, but the next term is going to be root R, which has to do with the length of this thing. So the first term, the leading term, is area. The next term is length of the perimeter. So we just keep that in mind for this elementary problem right now. But we're going to use it for the spectral problems. So that's you know, I mean, it can be formulated quite elementary like this, and it can be proved by a simple estimate like that. So now we're going to use this towards proving that this Boyle's law for boxes. I mean, going from here to Boyle's law for box is not difficult now. So let me just indicate that. So let's look at now a box which is 0a, b, and then the Dirichlet problem for this box was Laplacian of phi is equal to lambda phi, and phi restricted to boundary of, so this is our omega, boundary of omega is equal to 0, right? So this is the Dirichlet boundary condition. And the spectrum of this, we just derived, or I mean, I indicated last time, lambda and n is equal to pi squared times m squared over a squared plus n squared over p squared, and the corresponding eigenvalue phi mn is just the sine of pi mx over a sine of pi ny over p, and here m and n have to be strictly positive in order to avoid repetitions, right? So m and n, so belongs to n2, right? So the eigenvalue counting function in this case is closely related to this lattice counting function because eigenvalues are labeled by lattice points, basically. That's what it is, right? I mean, the lattice is not quite a square lattice. I mean, it's a rectangular lattice. So n of lambda is basically the set of, is the number of mn, I would say. Such that pi squared times m squared over a squared plus n squared over p squared is less than or equal to lambda. So this is completely similar to this case. As I said, so instead of circle, we have an ellipse here in this case, but the analysis is completely similar. So basically, number of rectangular lattice inside the ellipse. And exactly same technique works to show that basically, yes, this n of lambda divided, I mean, well, we have to divide by pi squared and take care of a and b. So what you get, you just get that lim of n of lambda over lambda as lambda goes to infinity is equal to area of omega. This of omega is here, divided by 4 pi, which is equal to AB over 4 pi. So in this case, Boyle's law is completely elementary estimate. I mean, that's that's exactly what people knew when Boyle started to prove the general theorem, and he had to use this result. So his idea was to approximate general domain by this sort of box-type domains from within, from outside. So we'll discuss the proof soon, but this is completely elementary in this case. Of course, you can go to higher dimensions in a similar fashion. But now, let me just mention a relevant, a related problem, and then indicate what happens in that case. That's the Neumann boundary conditions. So any questions, by the way? Okay.
I have a question.
Yes, could you speak a bit louder, please?
Yeah, so this kind of method only works when there's some kind of periodicity at the boundary, right? Because then you can tile the domain and make a lattice. Yeah. So it only works for tori and like other stuff?
No, that's it. This method really just works for tori.
Okay.
Yeah, even in this case, yeah, I mean, but there are analytic methods available that I will mention. So because when we want to prove this Milnor counterexamples, which is after all about tori, we have to prove something deeper about the spectrum, and that these elementary methods won't work in that case even. So we have to use very powerful trace formulas in that case. So that's yeah. But no, but I mean, I'm just giving this as a kind of warm up. And so that you get some feeling for the problem, so that we kind of hands-on approach to the problem. So,
thank you.
Yes. Okay, so now there is another boundary condition, which is Neumann boundary condition. So this is d phi dn equal to 0. So this is Neumann boundary condition. So it means this directional derivative d phi dn is gradient of phi by definition, and so we have this unit normal vectors, say outward, for example, and this is the definition. So it means that the gradient has to be orthogonal to the boundary at this point. And okay, so this is also a very important problem physically. This says something, okay, has to be equal to 0. So what are the eigenvalues and eigenfunctions? In this case, you get a little more eigenvalues. So in this case, actually, what happens is that phi of mn is equal to, but there is a cosine function. So cosine of pi mx over, say, a, cosine of pi ny over b. Okay, so, but in this case, m and n belong to n0 cross n0. So in other words, you can take 0, so, and lambda, so let me write it, lambda mn is equal to, I would say, pi squared times m squared over a squared plus n squared or b squared. So all of a sudden, all these points are also added to the spectrum. On this boundary and on that boundary. So in this case, 0 belongs to spectrum of the Laplacian, and 1 is the eigenvector of this eigenvalue 0, right? Is the eigenvector. zero eigenvalue. So this is unlike the case of Dirichlet, where the function itself had to be zero. In this case, the gradient had to be normal to the bound. All right. So otherwise, the other points are there. But in this case, again, you see the number of these lattice points again. So let ZR prime equal to number of lattice points again. But in this case, lattice contains these points. Again, if you take the limit by the area, it's going again to be equal to 1. So there is no difference because these sets of values here and here, they number compared to the number of all lattice points and compared to area. So this grows linearly, this grows squarely. So in the limit, the contribution from these eigenvalues, so this doesn't contribute. Those eigenvalues that one of them is 0, in the limit do not contribute to the limit. So this is equal to 0. So this immediately, by the same method, implies that actually Boyle's law is true for Neumann boundary conditions without any change. In this case, at least we verified that. So implies Boyle's law. For Neumann. A boundary condition. Right? So that's good.
So is it expected in general that Neumann boundary conditions will give the leading term the same for the
Yes.
bounding function, but the subleading term would be different?
The subleading terms, there will be a difference of plus minus 1. I'm going to discuss that now, right? Right. So there's going to be a difference between in the subleading term, yes. Yeah, as it was mentioned, in general, the boundary conditions boundary conditions doesn't matter in the while term, which is the leading term, the volume point. But in the subleading term, it makes a difference. So let me relate it to that. Actually, now let me write maybe a kind of exercise or something like that. Okay, so exercise is this. So part 1 is prove formula. So n of lambda equal to area of omega over 4 pi lambda minus length of boundary of omega over 4 pi plus root lambda, sorry, plus O of lambda, little o, where omega is this box. And here we are talking about Dirichlet condition, right? And second thing is that this term changes to plus 1 for Neumann boundary condition. you're adding something to the estimate here. But the appearance of negative one for Dirichlet, we kind of saw it actually, right? When we were estimating this. Oh, there is a comment. Let me just see.
The lambda is in the numerator.
Lambda is in the numerator, right? In the first term, lambda is in the numerator. Is it? Where is lambda? Oh yeah. Oh yeah. I'm sorry. Yes. Absolutely. Yes. Of course, it's growing. Yes. Thanks so much. Yeah. Great. Okay. So yes, that's the situation. To be honest, I haven't tried the problem myself. So, but I believe it's doable for the box. Of course, the general case, as I said, it took 70 years, and even still in some cases. I mean, under some condition on periodic billiard for the domain, not in general. So, okay, that's the exercise. Try that. Hopefully, you can do it. Okay. So we have now this. So now maybe related to this wild term for boxes, there is a famous problem which is called Gauss circle problem. Let me mention this because there is an open conjecture. There are a lot of work still people do. So this is Gauss circle problem. So this is really analytic number theory. So what's the problem? So yeah, let's introduce some quantities. Let R of n basically that's what we introduced over there, but now I want to be precise. The number of lattice points in all of Z2 such that n is equal to m1 squared plus m2 squared. So basically, so n is equal to 0, 1, 2, so. So for example, R of 0 is equal to 1, R of 1 is equal to, well, we can have plus minus 1 here, 0 there, or plus minus 1 here, 0 here, right? And then R of 1 is 2 times 2 is 4. Then R of 2 is also 4. R of 3 is not sums of two squares. So this is equal to 0. R of 4 is equal to 4. I hope I'm right. R of 5 is equal to 8. R of 6 is equal to 0. 6 is not sum of two squares. No. And so on. So this is a quantity that's basically tells you in how many different ways an integer, a non-negative integer, can be expressed as sums of two squares. This is something of interest for number theory. So let's then nu of x, which is of the form like lambda of x, this is sum of R of n. N is less than equal to x, bigger than equal to 0. This is equal to sum 1. We can write it as m1 squared plus m2 squared less than equal to x. And 1 and 2 belong to Z2. So now let's n of lambda. The eigenvalue counting function So for torus, so by this I mean the following problem, of course, and there is no boundary condition. So this phi now is from R2 to R. It's a periodic function. It has two periods, say 0L and 0L. I mean, in two directions as periodic. So phi of x plus L, say y is equal to phi of x y plus L is equal to phi of x and y for all x and y. So these are exactly, so of course, C infinity and periodic. So these are exactly functions from R2 divided by the square lattice, right? So divided by Z L cross ZL. So this is a torus to R. So what we did, we just took R2, divided it by square lattice. Is a discrete subgroup. And the smooth functions here are the same as doubly periodic functions like that. So there is no boundary condition because this guy has no boundary anymore, right? So we are now on the torus. So we constructed the torus, and now this function phi comes to R, right? So this is lattice, say, lattice is ZL cross ZL, right? So this is the torus. Okay, so this is the same Laplacian. It doesn't like X here anyhow, so that's it. So this one is a spectrum, again, is easy to compute. And in this case, you can see that the spectrum, so the Eigen functions are phi of Mn, xy, is basically exponential of 2 pi I, say, times x m over L plus y n over L. There's a little bit better way to write it, but that's okay. But now notice this time m and n can be anywhere in Z2. And so what are the eigenfunctions in this case? So the eigenfunctions are, okay, so let me erase this. Lambda mn, and not eigenfunctions, sorry, eigenvalues are exactly 4 pi squared times m2, I mean over L2 times m2 plus n2. So this is now labeled by all lattice points, not just in the first quadrant. Now you have a lot of those. So with respect to this function nu of x, of course, you can write it as you can write this n of lambda to be equal to nu of this is the area divided by 4 pi squared times lambda. So this is the relation between this analytic number theory problem and this spectral geometry problem in this case. It's very straightforward relation, right? So, of course, now, what we proved was that number of lattice points in the first quadrant divided by the area of the first quadrant circle goes to 1. But now, of course, same argument actually from the same argument, from the same result, you can get that the number of lattice points inside the circle divided by the area of circle as r goes to infinity goes to 1. That's plain. So that immediately gives you an estimate for this function using this relation and lattice counting. This immediately gives you an estimate for nu of x, which is the following. So in this case, Y's law then implies that limit of nu of x over x as x goes to infinity is equal to pi. So this result was proved by Gauss. Well, I mean, he didn't have to do much. He just did this elementary argument that we did. But actually, he also calculated the subleading term, the square root. So you may want actually to read Gauss's original paper. So this is due to Gauss. In this form, Gauss did it. He didn't look at spectrum of Laplacian. He just looked at number of lattice points inside the circle and take the limit. So this was done by Gauss, I think around 1830s actually. And so you just, the remainder term actually, so right then, I think he suggested actually to write nu of x essentially as pi x plus the correction term p of x. And so he asked about the nature of this term. So there is a very famous conjecture due to Hardy. It's Hardy conjecture. The conjecture is that p of x actually is of the order of x to the power quarter plus epsilon for any epsilon positive. I believe they can show that epsilon 0 is wrong. I believe this can be shown. I'm not 100% sure. But Hardy is asking for something just a bit more. Show that, okay, the difference goes to infinity, but no faster than x power quarter plus epsilon for any epsilon positive. So I believe the best result that's available here is following. I mean, this result already quite old actually. Maybe there are improvements. I didn't check this lately, but one really good result is due to Huxley, I think. I believe this is 1992. He showed that p of x is equal to O of x to the power 23 over 73 log of x to the power 315 divided by 146. So notice that 23 over 73 is just, and this is, I mean, in this scale of things, is way bigger than, of course, 25%. That's more or less what Hardy is asking for to prove. But I think by 1992 it was here. But again, there is also this term. But this term is it's less than any power of x anyhow. So that log term is less than any x power. So but that's so yeah. I mean, computing the subleading term and then after subleading terms, things can get very, very complicated. So it looks like there is a really very wild world out there that I think humans don't have access to. It seems it's just completely beyond our techniques, more or less. Somehow it's quite wild, the estimates after the subleading term. Okay, any questions, guys? Or? Okay, so now, as I said, so we did this example. Now, as I said, there is always this reference to kind of, can you hear, you know, the shape, or can you hear the eigenvalues, stuff like that. There is some musical connections that's always made. So let's see what does that mean. So I formulate this next section like this. Can one hear the eigenvalues, or I would say the spectral? So this is connections with wave equation and sound. Okay. So let's see. I mean, this is a very standard stuff actually. So let's look at the wave equation from physics or applied math, actually PDE even. Yeah. So we call wave equation. So in 1D, the wave equation is this UTT minus UXX is equal to 0. So what is U? So U is a function of two variables now. So at point X, like imagine you have a kind of vibrating string in one dimension, and this is the amplitude of the wave at point X at time t. This is U of t and x, right? So this was shown actually quite a long time ago by D'Alembert. If you assume that your vibrations is not too wild or too high, if there are small oscillations near the equilibrium point, then this linear equation is a good approximation to the equations that this wave has to satisfy. This amplitude function in this case has to satisfy. Of course, we are assuming that the speed of the wave is 1, but there's usually a coefficient here which is related to speed, but let's not worry about that. Okay, now in ND, of course, we have this again UTT. So in 2D, for example, UTT minus UXX minus UYY equal to 0, but you can write it as UTT plus Laplacian equal to 0. Now, again, I called minus UXX minus UYY my Laplacian. So in a lot of places, you will see wave equations written as UTT minus Laplacian equal to 0. That's because of that. Okay, so this gives you, now this is like for a maybe a drum kind of, so this is, imagine this is the drum head, and your drum, imagine, is clamped on the boundary. It's fixed to be 0. So the boundary condition is that U of t and x is equal to 0 for all times and for all x belonging to boundary of omega. And your drum can have maybe like a creative drum with some holes in it. That's okay. Right? So we have this as we discussed, but in a different way. Okay, so, x and y, I should say, sorry. But x could be two variables, that's okay, but anyway, that's, oh no. Yeah, no, that's okay. So, yeah, equal to 0, right. Ah, no, that's gone, sorry. For any x in the boundary. Oh, this x is not that x, sorry. Okay, so, I mean, how can we relate this, the wave equation, to Helmholtz problem? So actually, that's the way Helmholtz equation came about, because as I said, that equation is kind of hard to digest if you're just given as an eigenvalue problem like that. I mean, that's not the equation of physics per se. So relation to Helmholtz. Helmholtz, I suppose this is correct, equation. The argument here is that using that spectral decomposition theorem, for each time t, let's be formal, don't care too much right now about convergence of series or the sense of convergence of series. Let's just be formal and write it like that. So we can just say utx. Now imagine you are in two variables or one variable or n variable. It doesn't matter, but I generically write for utx equal to sum, ak p phi k x k from 1 to infinity. Now, the coefficients, so imagine this is an L2 expansion. So the coefficients, of course, changes with time. So it's a time-varying expansion, this one. And this phi k's we choose to be solutions of Dirichlet Helmholtz equation. In other words, is equal to this one. And phi k restricted to boundary is equal to 0. Right? Okay, so if you now, again, formally sub into the equation, you really get some equations for these AKs. And you see the relation between oscillations of the drum and the spectrum or Dirichlet spectrum, like this. So let's see. So then we get sum a k double prime phi k plus a k Laplacian of phi k has to be equal to 0. So we get sum a k double prime plus lambda k a k phi k equal to 0. Yeah, remember these lambda k's were bigger than equal to, were actually strictly bigger than 0. So, and of course, this has to be 0 for all t and x. So it means that a k double prime plus lambda k a k has to be equal to 0. And this has the solution a k t equal to, I mean, there are two solutions. I just picked one, which is e to the I square root of lambda k t. So the solution that we get is this: u of t and x is sum of e to the I root lambda k t, k from 1 to infinity, and then uk x. Right. So, well, now what are these guys? So these are standing waves in this picture. You see, you can write. So what this shows is that you can write the general solution of the wave equation as sums of standing waves. These UKs now have a meaning. They are standing waves, and they oscillate its frequencies, which are essentially a square root of lambda k. Right. So the frequency in UK is the square root of lambda k. So these are the important numbers now. So, and indeed, so the fundamental tone or fundamental frequency is the first one. The first frequency is the one that's most pronounced, in fact, and usually dominates. So fundamental frequency is nu 1, which is the square root of lambda 1. So this is the connection I just wanted to mention. I thought I should spend 5-10 minutes explaining, because people always talk about this, can you hear the shape of a drum, da, 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 but then we are always talking about the Helmholtz equation with Dirichlet boundary condition, or with Neumann, or other boundary conditions. But this is the reason that wave equation actually is very much involved with Laplacian. That's one connection between Laplacian and problems of classical physics, right? Now, the beautiful thing is that actually Laplacian is related to 3 fundamental equations, and each of those equations give you an insight into nature of Laplacian, so and nature of Eigen Functions and Eigenvalues in very, very different ways, actually. So this was the wave equation connection. The second one is the heat equation. So the first one, so let me write it as wave equation. So remember, I mean, this was like UTT plus Laplacian equal to 0. Now the second one is a heat equation. Is the UDT plus Laplacian again equal to 0. So the UDT is equal to minus Laplacian. Our Laplacian again is the positive Laplacian. And Schrödinger equation from quantum mechanics. So, I mean, I bar d psi dt equal to h psi. Now, this h, the Hamiltonian, is always p2 over 2m plus v. But now we just put v equal to 0, so this is a free particle, for example, but we don't have to. We can take general v and ask spectral decomposition and all that, but let me just, so this is a free particle, quantum particle. So this is, in fact, turns out to be equal to minus h bar squared over 2m. So this is h bar squared over 2m Laplace. Because p is really I is h bar. So if you square it, you get minus h bar squared gradient dot gradient, but that's exactly Laplacian with minus sign. H bar squared Laplacian. So it's this one. So yeah, so Laplacian appears in 3 different fundamental equations. Actually, one of them is quantum mechanical. I mean, one of them is quite modern. This is due to Fourier, you know. During French Revolution, this was even before. This was during, monarchs times, I guess. Whatever it was. This is around 1820. This is around 1750s. This is D'Alembert, right? And of course, this is 1920s, right? By Schrödinger. So Laplacian appears in this equation. Of course, Laplacian appears in many other equations as well, many other things as well. So for us, this is going to be a very, very important connection. I'm going to use it to drive Boyle's law and a lot of things for general manifolds and also other things. So, any questions or comments? Okay, so it looks like there are no questions. Okay, so maybe then I'll do one more example before we go to general stuff. That's spectrum of the disk. The actual drum, actually, I mean, the drum, really, right? So let's do that. Because things get very complicated, actually. So, spectrum of the disk. So this is x2 plus y2, say less than or equal to 1. It's the disk in the two-dimensional space, flat. Okay, so yeah, the equation is this now, Laplacian of phi k equal to lambda k phi k. So yeah, I mean, as you have seen, again, this is an undergraduate problem, really. So we have to go to polar coordinates. In polar coordinates. So if you go there, well, Laplacian is given by, I never remember this formula, of course, d2 dr2 plus 1 over r ddr plus 1 over r squared d2 d theta squared. That's if you do this change of variable to Laplacian, x equal to r cosine of theta, y equal to r sine of theta, you can drive this relation. With some work, actually, is not. So now I change, but I use the same notation again. Phi, I consider now my phi as a function of r and theta. I mean, it's going to be, I should introduce a different notation, but I just call it again phi of r and theta. Right? So to solve this equation, the method, which essentially that's what I used also before, is this separation of variables. It's a time-honored method. I think people here in physics know these things quite well. Phi of r theta, let's assume, let's consider this a special class as a product of two functions, a radial function and an angular function. So let's assume we get that. So then if you use this operator applied to this equation, equal to lambda phi, then you get the following, minus r double prime t plus 1 over r prime t plus 1 over r squared r t double prime is equal to lambda rt. This is the right hand side of this, and this is left hand side. Now, you have to divide by r and pull all t's in one side, capital R functions in the other side, then you get two equations, basically. And because they have to be, they are like functions of two variables that are equal to each other, so they have to be constant. So it follows that t double prime theta plus k squared t theta equal to 0. I mean, it follows that there exists k such that, I mean, we don't know the nature of k, but such that this holds. And also this holds, minus, yeah, sorry, r double prime t plus 1 over r prime t plus lambda minus k2 over r2 are equal to 0. Now, something tells me I've made a mistake here. I should not have a t here. And here, this t is extra. Yes. So what's going on? Yeah, no. I mean, there's no t here. So. Yes, that's that. Yes. Okay. Now this is essentially Bessel's equation. If you multiply by R2, I mean this multiplied by R2, you get R2, R double prime plus R prime plus yeah. So yes, R2 lambda minus K2 R equal to 0. Now, this is Bessel's equation. So this Bessel function and Bessel's equation, or I should say Bessel functions and Bessel equations, is so fundamental in mathematics. It's amazing in how many different places the equations arise. So this is Bessel's equation. So I just write it in standard form, x2 d2y dx squared plus x dy dx plus x2 minus alpha 2y equal to 0. So one solution, which is called Bessel function of the first kind, j alpha of x. So alpha is a parameter. In this case, is essentially J2 over lambda or something like that. So this is a Bessel function of the first kind. And it is known that this function is actually bounded near 0 if and only if the function is bounded near 0 if and only if alpha is an integer. So in that case, and we are looking for bounded function R because we are looking at vibrations of this drum, right? And we cannot allow the vibrations, the oscillations explode at zero. We want a regular function, really a smooth function inside and continuous up to the boundary. So we need this to be analytic, or I mean to be at least bounded. So it's bounded near zero if and only if alpha integer. Okay, so this immediately implies that this k belongs to z. Has to be an integer. Okay, so once we get that, now we get a series of solutions like this. So we get these solutions phi of r and theta equal to tk of theta, jk of the square root of lambda r. This is the Bessel function. Well, tk, the radial part, is equal to ak. I mean, this equation is like a harmonic oscillator equation, or yeah, this is easy. So I mean, classical equation. So ak cosine of k theta plus there's a general solution bk sine of k theta, right? So let me draw these Bessel functions for you. So we have to know all these Bessel functions now. So J0, J1, so on. So you can check your Wikipedia page or whatever source you like. The Bessel functions each of them has infinite number of solutions, and they oscillate. So the first one actually is not zero at zero, but the other ones start at zero. I think I just made a blunder with this drawing, but that's okay. J0, J1, J2, and so on. So the point is that these are actually entire functions in the plane, even as a function of complex variable. They are analytic in the entire plane. They are entire functions. In particular, they are smooth on the line. Infinite number of solutions. Zeros. Each jk has infinite zeros. So we sum in, but now notice we want to have a Dirichlet boundary condition, for example, right? So we want to have this jk of root lambda equal to 0, right? So this implies that root lambda, so and this is the spectrum, right? I mean, that's what we are looking for. So it implies that root lambda belongs to set of zeros of J0, J1, of J0, or I should say, or J1, or J2, or J3. So it's the union of the set of zeros of all these functions. So it's really like it's here, 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 here. So all of a sudden, you notice a spectrum of a drum. You notice how complicated an object is, actually. You have to take all Bessel functions, entire Bessel functions, plot their zeros, all of them, and that's the spectrum. I mean, this is quite complicated object, right? Compared to a spectrum of a string, which was actually, as we notice, in fact, is just in arithmetic progressions. It's like 1, 2, 3, 4, da, da, da. So these are like, they progress in arithmetic way and very regular. You have the fundamental tone and the overtones, right? But here the fundamental tone is the first one, but the overtones are not multiples of this. They are just crazy roots of this things. I don't want to use the word random because the word random scares me. I mean, I don't know what it means really in this case, but it looks quite wild at least. So the first eigenvalue, lambda 1, is computed to be, it's the standard, alpha 0, 1 divided by, so 1, or alpha 0, 1 divided by A. A is the radius of the circle. I mean, we dealt with circle of radius 1, but if you have circle of radius A, then this has to be 0 at r equal to A, so this becomes this one. So alpha 0, 1 is first 0 of J0. It's a well-known number. Alpha 0, 1 is equal to, I believe, 2.45. So for a vibrating string, lambda 1 is equal to pi over A. You see, this is for disk vibrating drum of radius A, this one. But for a vibrating string, violin string, for example, in very kind of simple approximation, this is going to be lambda 1 is equal to pi over A. Oh yeah, anyhow, I have it here, sorry. This is the first eigenvalue of vibrating string, but this is the first eigenvalue of of vibrating drum. This is a smaller.
I have a question.
Yes, please. Oh, there are two questions actually. Yes.
Yeah. Why are we looking for zeros of the Bessel functions? I mean, if the eigen function is a multiple of the Bessel function, then if we get a 0 of the Bessel function, isn't the entire eigen function 0?
No. We are just looking at the values such that on the boundary it's equal to 0.
Oh, okay.
Yeah, because we want to have, remember, we want to have this function phi of 1 and theta equal to 0 for all theta, right? We want it to be 0 on the boundary, right?
Mm-hmm. Yes.
And this, if you sub in, where is my equation? You get that jk root lambda has to be equal to 0. Right? So it should be
yeah, I understand.
Oh, condition k integer. Yeah, I think in the first term lambda is in the numerator. Oh no, that was condition k integer comes from requiring that t theta is periodic. Oh yeah, okay. So I think that's correct. Yeah, maybe. So what is the behavior? Plus age, can you tell me the behavior of J alpha near 0? It's x to the power alpha. But that's not, so you see, if alpha is not integer, x to the power alpha is not regular at 0. We still want to have a differentiable function, right?
Yeah, but it's not, it is bounded, I mean, for...
At least it's bounded, right? I mean, I said it's not even bounded, yeah, but it is bounded. Okay, I forgot about the nature of this jk's near 0. But if it is like some x to the power alpha and alpha is not an integer, I mean, it has to be positive because otherwise it's unbounded. But then even is not the smooth. But yeah, but from actually that's a very happy situation because this condition alpha integer actually implies that this one is also periodic because we need this to be a continuous, I mean, to be a smooth as well. I mean, this function, you know, has to be 2 pi periodic, and for that, k has to be, I mean, essentially has to be an integer. So you can get it from there too. Any other comments or questions?
I have a question, please.
Yeah. Could you speak louder, please?
I am trying. I hope so.
Okay, sure.
So I am not sure that Euclidean metric and hyperbolic metric induce the same topology on disk without boundary?
No, I mean, hyperbolic metric, you can look at Laplacian in hyperbolic metric, but it's going to be very, very different nature. Its form is going to be...
The topology of unit disk, I mean, is the same for both matrices, right?
Oh, topologically, they are the same. Yeah, of course. I mean, yeah, I mean, exactly. Yeah.
So do we make it complicated if we do the same thing and use 1 point compactification of unit disk?
So if you use, well, I mean, that metric, you see, these spectral geometry arguments, most of them work really in the compact case, and this hyperbolic plane is not compact. So a lot of things can fail. I mean, even a spectrum is not discrete in that case. Actually, spectrum of Laplacian in the hyperbolic plane is a very interesting object, but it has continuous spectrum and discrete spectrum too. Maybe we'll look at that maybe sometime, but it's very complicated thing. Now, if you go to 1 point compactification, I believe this metric does not, extend to 1 point compactification. I mean, it's still a conformally, it's like maybe.
Oh, yes, you're right. Oh, it blows up when you get close to the boundary.
We close the boundary, but then you see this in the hyperbolic metric, as you approach the boundary, distances go to infinity, actually.
Yeah, I mean, by blowing up, I mean that when you reach to the boundary, it goes to infinity.
Yeah, you go to infinity, yeah. I mean, then you're dealing with a non-compact space, right? And the spectrum in that case, yeah.
Okay, thank you.
It's very, very different. Maybe we can discuss it later on. If you ask me, I'll be happy to discuss. Yeah,
okay,
sure.
Thank you.
Okay, very good.
I had another question.
Any other questions?
Yeah, I had another question.
Yes.
The Bessel equation that you wrote is a second order linear ODE, right? So it should have two linearly independent solutions for every alpha?
Yes. So what about the other one you're asking, right?
Yeah, because if we have two of them, then we don't need one of them to vanish, right? We just need the linear combination of them to vanish at the boundary of the disk.
Yeah, but the other one actually blows up at the origin, I think.
Oh, okay.
So that's not good.
Okay.
Yeah, that's why, yeah, exactly. My understanding is that this is the only one that's regular, has a chance of being regular at 0. The other one is not regular. You see, this equation that I wrote, it has a singularity at 0. I mean, so because there is x squared d2y, so you cannot have two regular solutions at 0. I mean, that 0 is a singular point of the equation. It could be it's a regular singular point. I forgot my ODE now, but I know one of the solutions is actually unbounded at near 0 for all values of alpha. And in fact, yeah, I mean, yeah, okay, right.
Thank you.
Good. Thank you. Yeah. Any other comments or questions?
Yeah, sorry, probably I'm thinking of something very wrong, but it seems to me that, so if you consider an eigenvalue, an eigenfunction, and then you consider the rotation, then because rotation is sort of keeps the Laplacian, it sort of gives you another sort of eigenfunction, right?
Yes.
And so doesn't this imply that the eigenfunctions should be sort of, shouldn't depend on alpha?
No, you see, the thing is this. if you have an equation that has some symmetry, the solutions do not necessarily have the symmetry, right? It may have part of the symmetry, but they are not necessarily symmetric.
Okay.
I mean, for example, consider the equation like y prime equal to y. I mean, this equation has kind of translation symmetry, but its solution is e to the x, is not translation invariant, right?
Oh, yeah, that's true.
Right. So you have to be careful about the symmetry. The symmetry for the equation does not imply symmetry of the solutions.
Okay.
Yeah. But
Okay,
what it
interesting.
implies, but it is still important. That's an important question. But what it still implies is that if you have one solution and apply Laplacian, apply the rotation to it, you're going to get another solution. Send solution to solutions.
Okay, but these two solutions have the same eigenvalue, right?
Yes.
But didn't you say that for every eigenvalue, there is only one solution?
Oh, no. In this case, no, I don't think so. In this case, there is going to be multiplicities. Actually, I'm not sure. No, I think there are multiplicities. Actually, I'm not. About multiplicities, yeah, you have to check. Yeah, Wikipedia has very nice set of eigenfunction solutions. I mean, in this case, so let me not say anything because I may kind of incriminate myself if I say something which is wrong. So let me think about it. I answer your question. Yeah.
Okay, thanks.
Thank you. Yeah, no, that was a good question. Okay, so yeah, the drama is kind of dramatic. Yeah, you can say that, I suppose. Okay, so now we can start looking at Riemannian manifolds and kind of prepare ourselves for lifting everything to Riemannian manifolds. So Laplacian for Riemannian manifolds. So now we are going to say our drums are going to be, so we are going away from these domains and look at general Riemannian manifolds and see the spectral problem there. So first we have to understand Laplacians. Okay, so the conditions to do this is Riemannian. So let's assume that Mg be a Riemannian manifold. So the metric is G, but then I have to assume at first at least a little more. So I assume there is an orientation also, plus orientation. Okay. So this G, Riemannian metric, of course, in local coordinates, you can always write it as Gij, dxi, dxj, ij from 1 to n. But it's always a good idea to use, and actually what I will do, to use Einstein's convention and just write it as Gij, dxi, dxj. So summation over repeated indices down and top is understood. So in local coordinates, and then using this, so let's assume that G, so determinant of G is determinant of this matrix Gij. Okay, So I also need the volume form. So you can use the orientation, and you can use the metric to construct a top n form, which is nowhere zero, and that's the volume form. So I denote it by d vol g, which is again in local coordinates is square root of determinant of g, dx1, veg dxn, right? So it's a good idea to brush up a little bit basic Riemannian geometry in first chapter in the book, Riemannian geometry. You can get your hands on. So in local coordinates, I mean, I should say in oriented local coordinates. Because if you don't stick to oriented coordinates, if you change the coordinates, you may get the wrong change of sign. So, but if you stick to same orientation class in different coordinates with the same orientation class, then you get a well-defined n form. So my notation now is this. I just write C infinity of m to be the set of all smooth functions to C. I mean, you can look at real valued functions as well, but just let's look at complex valued functions. It doesn't matter. So f belonging to C infinity. So another notation for this is omega 0 of n. We call these things as zero forms. And also, you can also just sometimes maybe see C of n inside C infinity of n. So these are compact support functions, for example. You can also look at one form. So my notation, so omega p of n, smooth p forms. Now, there is a little bit of inconsistency here, because usually when people talk about forms on manifolds, they don't consider forms with complex coefficients. But my zero forms have complex coefficients, namely they take complex values. So I hope you forgive me for doing this. So you can here just look at f going from m to r, and then I would be consistent. So a smooth p forms. So obviously p goes from 0 to n, and that's dimension of n, right? So then you have this Durand complex. Which is omega 0 of n, is d exterior derivative, omega 1 n, d omega n n. So you go to 0 and you, so this d exterior derivative So, for example, on functions, it's almost like a gradient. Of course, gradient is not the right word in this case, because gradient gives us a vector field. We are in dual situation. We are in one forms. So gradient, it's okay. So we'll discuss. df is equal to sum df dxi I from 1 to n. Again, this is in local coordinates. Okay, so that's so we have that, and you can uniquely extend it. So this, of course, t squared is equal to 0. So this is really complex, and its cohomology, of course, is the wrong cohomology. But I don't need it that right now. So, but now what we need is this star operator. So encourage you to just take just maybe 1-2 hours or something. You study this Hodge star and the D star, Hodge star operator. So this star now basically takes us from P forms to n minus P forms. This is completely a linear algebra operation. I can discuss it, but I encourage you first to read the definition because it's pure linear algebra. I mean, what you do, you just use metric and orientation. Construct this. Then you get this star, which takes you from omega p of m to omega p plus 1 of m. You see, D increases the dimension, or rather the degree of the forms. D star decreases the degree. It's like that. Sorry, p minus 1. So what is this D star? D star is, now, I don't remember the sign. There's plus minus here, I suppose. There is this star, D star. This star is here. And this is, okay. So that's a kind of warm up for kind of some tools we need that we are going to use next time. So some sort of basic differential geometry and yeah. Okay, I think my time is up. I even went over time. Sorry about that. So do you have any questions or? So yeah, I mean the YouTube channel for now is just private. I will post the lectures there, and then we will make it public even. Why not? And so Babak, our TA, is kindly typing some questions just for self-study now. And also he's going to type his lecture notes, and hopefully all of us can work on lecture notes and make it into some nice set of notes. So, but the original, the first version is coming to you very soon. So maybe by the weekend or something. So thank you so much, guys. Yeah. If you don't have any questions, I'll just stop. Okay. Stop recording this.